Hey there! So today we're going to go a little bit further beyond the ideal gas law, and we're going to begin to manipulate the ideal gas law to suit our whims. We are going to manipulate it so that we can get a couple of other different factors out of the ideal gas law. The first of which that we are going to be looking at is the density of the different gases. Now remember, density is mass divided by volume. You've known that probably since junior high. But with gases in the ideal gas law, PV equals nRT, there's a whole bunch of factors that can go into changing the density of the gases. So for instance, pressure. If we take our pressure that's there and we crank up the pressure to high pressure, then we can lower the volume, and that is going to affect the density or how packed those particles are. So the pressure is going to be involved. The temperature is going to be involved, because remember, if you have a low temperature and then start to heat something up, right? If you heat something up, then those particles are going to move around even faster, and if given the opportunity to, they're going to spread out, and so the temperature can affect the density of it as well. Even the substance itself is going to affect it. So for example, in each of these cases, you can see that you've got something like helium, and helium is going to take up a certain amount of space or have a certain mass that is there. But compare that to something like carbon dioxide that is a bigger molecule in the same space. Even if you have the same identical number of pieces in each of those boxes, it's pretty clear that this guy over here in red is going to be at a higher density, and this guy over here in the blue-green is going to be a lower density because of the size and the mass of the molecules that are there. So basically what we have to do is we have to recognize that density is the mass per volume, and we're going to manipulate the ideal gas law, PV equals nRT, until we can get mass per volume. And then we're going to find that it has all those other factors that are involved. So our first trick in this is to recognize that N, the number of moles, is the mass divided by the molar weight, the molecular weight. So grams divided by the weight from the periodic table tells you what the number of moles are. So I'm just going to do a simple substitution here and take N out of the equation and instead put in grams per molar weight. So now what I have is I have PV equals grams per molar weight RT. All right, I don't like that molar weight being on the denominator, so I'm going to multiply him across, and now I have the pressure times the volume, which is him and him, times the molar weight, right? And then that's going to be equal to the grams that's there, RT, which is here, here, and here. So now what I'm really looking for is the density, but remember that the density is the grams divided by the volume. So if I divide out the volume out of these guys and get grams per volume, then I end up with the following equation. And the following equation for density is the grams per volume, but it's the pressure times the molar weight divided by RT. Now they will not give you this equation on the AP test, but they will give you the ideal gas law. So you're going to have to make sure that you know how to generate this equation from the ideal gas law. This is not going to be on the equation sheet. So you've got to know that the density is equal to the pressure molecular weight divided by RT. You should be able to manipulate PV equals nRT to get that equation right there. Now, armed with it, it just becomes as easy as the last topic that we had, which is just kind of plug and chug. So this one here says, calculate and compare the densities of hydrogen gas to sulfur hexafluoride gas at STP. So again, our density is going to be equal to the pressure times the molecular weight divided by RT. Now, it says that we are at STP, so I'm going to choose a pressure to be 1 atmosphere. Let's go ahead and do hydrogen first. So this guy here is hydrogen. So the molecular weight of hydrogen is 2 grams per mole. And then R, because I chose atmospheres, I'm going to use 0.0821, and that's in liter atmospheres per mole Kelvin. And then because it's at STP, that's going to be 273 Kelvin. So at that point, I get out my calculator, and I have 2 at 0.0821 at 273. Gets me a density of about 0.0892, and that is going to be in grams per liter. 0.0892 to 3 significant figures. Now, sulfur hexafluoride is going to be the exact same thing, except you're going to have a different molecular weight because the pressure is the same. That's 1 atmosphere. R is the same. That's 0.0821. That never changes because it's a constant. And that's liter atmospheres per mole Kelvin. The temperature is 273 Kelvin. So again, here, and here are the same because you're at the same conditions. The only difference is that you're dealing with sulfur hexafluoride gas instead of hydrogen. So sulfur hexafluoride has a mass of 146.1 grams per mole. And so this is going to be the same exact thing except with 146.1 in for the mass instead of 2 that's there. So it's 146.1 divided by 0.0821 and the 273. So that has a density of 6.52 grams per liter for that. So sulfur hexafluoride is way more dense than hydrogen gas, which makes sense because it's 70 some odd times heavier than hydrogen gas because the molar masses are so wildly different. All right, so number 2 here is the same thing except that we're giving you a bunch of other units. So I want the density, and the density is going to be the pressure times the molecular weight divided by RT. So the pressure, I'm going to go ahead and put in 780 millimeters of mercury because they gave that to me. The molecular weight of carbon dioxide is 44 grams per mole. So again, that stuff weighs 44. My R is going to be my 6236 because I am in millimeters. So that's going to be liter millimeters of mercury per mole Kelvin. And then my temperature is 243 Kelvin because I am at negative 30. So 243 Kelvin, that's there. So this is just a plug and chug. The density now is 780 at 44 divided by the 6236 and the 243 gets me a density of about 2.26 grams per liter. All right. What if instead of looking for the density, we are going to go straight towards the other hidden factor in here, which is the molar weight of the gas? What if we don't know the gas that we are interested in? So all we're going to do is we're going to take this equation, and instead of solving it for the density, the grams per volume, we're instead going to solve it here for the molar weight. And so if we rearrangeify this equation, then we get that the molar weight of a gas is going to be equal to the grams RT divided by PV. So again, I shouldn't have to prove that to you because again, it is just a remanipulation of our ideal gas equation. We have PV is equal to nRT. I'm going to take N and divide it by the grams, change it into the grams divided by the molar weight, and now I'm going to solve for the molar weight. So that means I'm going to get the GRT divided by the PV with the molar weight moving up there, depending on how you want to deal with the conversions. So the molar weight is the grams times RT divided by PV. Again, they will not give you this equation. They will expect, if they're going to do this, that you can rearrangeify the ideal gas law equation to get this equation. So past that, it's just a matter of plug and chug. So what have we got here? We've got a sample of gas. And see, the molecular weight is going to be the grams. They gave that to me. That was 84 grams. R, I'm going to go ahead and use 0.0821 for liter atmospheres per mole Kelvin because they gave me atmospheres. T, the temperature is 473 Kelvin because they gave me a temperature of 200 degrees Celsius. So that would be 473 Kelvin that's there. And then I'm going to divide that by the pressure, which is 1.1 atmosphere, and the volume, which they gave me as a 30-liter container. So this is not hard. This is plug and chug once you know how to manipulate the equation to get what you want. So that's 84 at 0.0821 at 473 divided by that, and that gets me a molar weight of about 98.8 grams per mole for the molar weight. Last one. Same thing here, except that they have incorporated a little bit of other material from before. So, what did I tell you here? I told you that it's 85.7% by mass carbon and 14.3% by mass hydrogen. Okay, great. Now what we've got here is we've got a hydrocarbon tower like you would see if you drive down by the Joliet refineries. You see those giant towers. What's going on is you take crude oil and you send it through, and that crude oil gets heated up, and then the different weights, the different molar weights of the gases have different densities, and they are pulled out at different temperatures or different heights away from the heat source. And you'll notice that the higher you go, the fewer the carbons that you have, the lower the molar mass, the less dense the substance is. So up here you have very light hydrocarbons that might only have 1, 2, or 3, or 4 carbons. Down here, for things like fuel oil, you could have hydrocarbons that have 75 carbons in them. And so those molecules are going to be ginormicon compared to the ones that are at the top. And so they are going to have a higher molar weight and a higher density there. So what I have done is I have told you that the substance is 85.7% by mass carbon and 14.3% by mass hydrogen. You should think back to last unit when we did empirical and molecular formulas between these guys. So this guy here, I'm going to assume that I have 100 grams of this, and if I do, then that's that many grams of carbon and that many grams of hydrogen. And then I'm going to take this and I'm going to divide it by 12 grams, and I'm going to take this and I'm going to divide it by 1 gram. And I end up with 14.3 moles of hydrogen, and I end up with 7.14 moles of carbon. So your formula is carbon 7.14, hydrogen 14.3, but remember that's silly. So what you do instead is you divide by the smaller of the two numbers, so you divide by 7.14, and so you end up with a ratio of CH2. Now, remember, that's empirical. So it could be CH2. Actually, it can't because you can't draw CH2. But it could be C2H4. It could be C3H6. It could be C4H8. Heck, knowing this tower that's up here, right, if it's in the fuel oil area, it could be C70H140. Nothing is stopping it, all right? So the question becomes, which of these is it? And I won't know until I know a little bit more past the empirical formula. All right? So what am I going to do? Well, what I'm going to do is I'm going to come up here and I'm going to take the rest of the information and I am going to solve for the molar weight. So the molecular weight is equal to GRT over PV. So let's go ahead and do that. Let's see the grams. It said it was 533 grams. R, let's see. I got millimeters of mercury there, so that's going to be my 6236 liter millimeters of mercury per mole Kelvin. GRT, it said it was 225. So 225 and 273 gets me 498. So my temperature is, I guess, 498 Kelvin. And then I got to divide that by the PV. So my P is 740, a little bit less pressurized. And my volume was a 100-liter tank. Again, all of these things are here in the problem that they give you. Again, can't be in Celsius, you got to be in Kelvin. So all I have done is I have taken each of these guys and I have plugified them in. So if you plug all of this in, 533 at 6236 at 498 divided by your 740 and your 100 liters, you should get about 224 grams per mole is the molar weight of this gas. Okay, well, how does that help me? Well, remember that my empirical was CH2. Now my molecular is 224. Well, what does CH2, what relationship does CH2 have to 224? Well, how much does CH2 weigh? Carbon is 12, and then that's 2 for the hydrogen, so that's 14. So, which one is it? Well, if it was C2H4, then it would have a mass of 28. If it was C3H6, it would have a mass of 42, and so forth and so on down the way. So 224, if I divide that by my 14 that I got there, I get an answer of 16. So really what we're talking about here is C16H32. It is the 16th copy, or the 16th largest multiple of that number 14 there. And 16 carbons and 32 hydrogens should give you a mass of 224. So all I did was I took the 224 and I divided it by the empirical, and I got 16 out of it. And again, 16 would be 16 carbons and 32 hydrogens. So what kind of substance is this if we're talking about a mass of 16 carbons? So 16 carbons would be in the end of the kerosene to the start of the gas oils kind of a situation. It would be somewhere in there. So that would be what's going on with this guy. It would be a what? A light gas oil or a heavy kerosene, I suppose, in there. It would be one of those. So that's how you work those problems. So this is the same thing. We calculated the molar weight, and then I gave you mass percentages, and then between the mass percentages you can get the empirical, and the molar weight you can get the molecular. You can figure out what copy of it